So our next speaker is Linda, who is going to talk about the reverse mathematics of Borel combinatorics.
So thank you for inviting me. Thank you for the chance to come to Lumini again after a while. It's great to be anywhere after the pandemic, but especially great to be in Lumini. So today I'm going to talk about some joint works with Henry Tausner and Rose Weishar, but in order to introduce it, there is also a lot of background, so I'll just try to attribute as appropriate. All right, so I want to talk mainly today about some theorems of Borel combinatorics whose reverse math strength I would like to understand, and some small progress made in the direction of understanding these theorems. So to start off, there is a fact which both parts A and B of this fact, as far as I know, are folklore. So if you happen to know a reference for B, I would enjoy hearing. So it's well known that anytime that you have a graph that has no odd cycles, then it has a 2 coloring. And a proof is a very simple one. In every connected component of the graph, pick a place to start, color it blue, color its neighbors red, color its neighbors blue, and so on. And because you have no odd cycles, you'll never run into a problem by coloring in this way. That proof, although well known and very simple, actually uses the axiom of choice in the very first step, which is in every connected component, pick a place to start. So you could imagine that if you have some very large, some graph whose set of vertices is actually some very large space, there might be like many, many connected components. And indeed, it's well known that if you try to do the same thing in the Borel context, it doesn't work. So there is a Borel graph that has no odd cycles, but that also cannot be 2-colored in a Borel way. And so here is one standard proof of this second fact. So consider the unit circle and consider an irrational rotation on the unit circle. And for any pair of elements on the unit circle, just put an edge between them if you can get from one to the other by a single one of that rotation. Now, suppose for the sake of contradiction that we had a Borel coloring of this unit circle. Well, if it were Borel, then in particular, it would be measurable. Right. So what this is showing actually is that there's not going to be any measurable 2 coloring of this graph. Because any measurable coloring is kind of clumpy. You would always have some interval on the unit circle with 99% of what's in that interval receiving the same color. And then because the rotation is irrational, there will be some way to iterate it an odd number of times to get that interval more or less approximately intersecting itself. And so then you'll have because the interval is 99% one color, once you rotate it around an odd number of times so that it mostly intersects itself, you'll have something in there that it has one color and also it's odd number of shifts of it like has the same color, which well, we can't have that because if you think about what the orbits for this relation look like, it's just copies of chains like Z, right? So if you're going to 2-color it, you have to go, red, blue, red, blue, red, blue. So when something is an odd distance away, it has to be the other color. Okay, so this is a pretty standard proof via measure, right? Actually showing that there is no measurable 2-coloring for this graph. But the exact same argument can be used with bare category instead. Right? Because bare category also has this kind of clumpiness property. You would have like some interval where one color is co-meager in that interval, and then you can do the same thing with shifting it around. All right, and so notice that the important point here again is that we are considering graphs whose set of vertices is large, and so even though the graph, each component of the graph is countable, there is this sort of whole Polish space full of components that the difficulty with doing it in a Borel way is that it's hard to figure out where to start in each one. Okay, so this is one fact about descriptive combinatorics, and the part B, the part about the situation, what happens for Borel sets. It can be proved using a measure, or it can be proved using a category proof. All right, here's another theorem of descriptive combinatorics. So recall that if you have any graph, by definition, perfect matching is some subset of the set of edges of the graph, so that every vertex of the graph is included in exactly one edge. All right, so Hall in 1935 showed that anytime that you have an n regular graph with no odd cycles, that graph will have a perfect matching. And so n regular just means that every degree has exactly n edges coming out of it. He showed this for, I think, for finite graphs, but using compactness argument, you can extend that to a countably infinite graph very easily. And so by the axiom of choice, again, if you have an n regular graph, now imagine it on some large space. If you just look at each component individually, each component does have a perfect matching. And so again, if only you could figure out a way to orient yourself on the component, then you could find perfect matching component by component for the entire graph. However, it turns out that you cannot do this in a Borel way. So the first to prove this for all n was Marx in 2016. It had been known just for even n, even numbers n prior to that. But he showed that for all n, there's a Borel n regular graph that can even be acyclic, actually, so simplest possible kind, that nevertheless has no Borel perfect matching. And the interesting thing was that the proof of that theorem used Borel determinacy, which is an extremely big hammer as far as techniques are concerned. And so it was open for a few years, and he was asking, whether there could be a simpler proof of this theorem. For example, a proof that used measure, a proof that used category, because most theorems, when people try to take some kind of graph combinatorics and turn it into like a Borel version of the theorem and see whether it happens or not, most of the methods are these measure methods or these category methods, right? So the question came up: can this be done using measure or category? And indeed, just recently, Kuhn did prove the same theorem, at least for n equals 3, which was the hard case, using a measure type argument. Before that, however, it was known that at least if you wanted to do a category type argument in order to prove this theorem, your category type argument would at least have to be a little bit weird. So why that is, remember on the previous slide, this theorem showing that you can't have a Borel 2 coloring on the unit circle, it actually showed the measure path to prove that theorem actually proved a stronger theorem. It showed there's no measurable 2 coloring. And the category path to prove this theorem proved the stronger theorem, that there is no coloring that has the property of bare. So for this one, it was already known that anytime that you have an n regular acyclic Borel graph, that it would already have a perfect matching that had the property of bare. So the simplest proof via category of just showing that there is no Borel matching just because there's no category matching, that simplest proof could not work. But one could still wonder if there is some other way, some more clever use of category that could be used in order to prove this theorem from a category method. Then the last example that I want to share for motivation is Brooks' theorem. So suppose that I've got a graph where every vertex has a degree at most n, but the graph doesn't have any n clicks in it. So Brooks in 1941 showed, at least for the finite version of this, that there is an n coloring of the graph in that context. Once again, some compactness argument can tell you very quickly that it will work for an infinite graph with this property as well. So Marx has also shown that there's a Borel n regular acyclic graph that has no Borel n coloring. So in other words, this Brooks theorem also fails if you try to do it in the Borel context. And this is a proof using Borel determinacy. But around the same time, they also learned that if you were to try this to prove this theorem using either measure or category via the usual method would fail, right? Because they have shown that every Borel and regular acyclic graph actually has a measurable n coloring, actually has an n coloring that has the property of Baire. Right, so the reason that there is no Borel n coloring, if it's going to be because of measure or category somehow, it's not going to be that, because of it directly. All right, and so then a question that naturally arises, well, is there any way to prove Mark's theorem via measure or category? All right, so this is kind of the motivation or what I want to see. And also at any time, please interrupt me with questions. So I like them at any moment. Okay, so most people here are very familiar with reverse mathematics, but just a couple of slides for those that may be seeing it more recently. So reverse mathematics is a framework in which one can answer, at least in theory, the kind of, one can formalize the kind of questions that I was asking on the previous slide. So one of the founders of reverse math, Friedman, has this nice quote: "When the theorem is proved from the right axioms, the axioms can be proved from the theorem." And the idea behind it is, suppose that you have an axiom that can be used to prove a certain theorem T. Throw away all the axioms. Okay, don't throw away all the axioms, but throw away most of them. Just keep some very small little axioms that are just enough so that the theorem still makes sense. And then using those little axioms and the theorem, try to reprove the axiom, right? So you reverse the role of the theorem and the axiom. That's where the name reverse mathematics comes from. So if this works, if you can do this, then that's understood as a proof that that axiom was actually necessary in order to prove the theorem. Because using the theorem to prove the axiom shows by contraposition that if the axiom is false, then the theorem is false as well. On the other hand, if you want to show that some other axiom cannot be used to prove a certain theorem, then what you have to do is create what's called a separation, which is a model of mathematics, which I'll explain more in the next slide, in which the axiom B is true, but the theorem that you're trying to prove is false. Right? And so that's considered as a way of showing that that axiom is not able to prove the theorem, at least by itself. So what do I mean by a model of mathematics? Well, it turns out that most mathematics can be carried out in second-order arithmetic, which is a system in which we have two kinds of objects with natural numbers and subsets of natural numbers. This may not seem like a very rich system, but through coding, you can actually include almost all of mathematics in this context. So for example, I'm talking about theorems involving Borel sets, and you can encode a Borel set into a subset of the natural numbers. And you think of the subsets of natural numbers as just infinite sequences of bits. So you're just like coding like with some kind of computer code. And so if you want to give a code for a Borel set, well, what you actually give is a code for some countably branching tree that basically describes the sequence of intersections and unions that you performed in order to build that Borel set out of open sets. All right, so every Borel set is made from open sets by taking countable intersections, countable unions, and complements. And if you want, you can push all the complements to the leaves, so you can make a tree that just has intersections and unions at its nodes that tells you how to build the Borel set. All right, and so then these kinds of things, collections of natural numbers and then subsets of natural numbers, will be our models of mathematics. And then there are some axioms that go with these. So this whole system is called second order arithmetic. So I'll abbreviate that SOA later. Okay, so that's the background on reverse math. So let's talk a little bit more now about Borel set membership. So suppose that we have a Borel set and we want to know, and we have some element X, and we want to know whether X is in or out of that Borel set. Well, there's a sort of procedure of sorts, right? But I put procedure in quotes because it's not totally algorithmic. Sorry, it's not a computable procedure, but it is algorithmic in some sense, which is that you want to know whether X is in the tree. Well, if your tree is just a very simple tree, just a leaf that's saying like, well, actually I am just open or I am just closed, then you can just check in a computable way whether X is in that or not. But then you can sort of go by recursion for the other sets that were built along the way to building your Borel set. And say at every set that you encounter sort of along the way to building yours, well, if you want to know whether X is in there, well, if it's a union node, then you just check to see, check what you've already done to see whether X is in any of the sets that are being unioned there. And similarly, if it's an intersection node. All right, but the tree, of course, may have a very large rank, right? So this is a transfinite recursion process. But a single step in this process is arithmetic, or uses just like a finite number of Turing jumps in order to do a single step. So the axiom of arithmetic transfinite recursion basically states that in this situation where you want to do a transfinite recursion along some ordinal, that's a valid thing to do. Like that will, the object that is created by that process is actually an object that exists. That's one possible set existence axiom in the reverse math context. And that object that you create, we give it a name of evaluation map. All right, so for every X that you want to know whether it's in or out of the Borel set, there is an evaluation map which summarizes all of X's membership facts in all of the sets that we're building up to creating the Borel set that we're talking about. All right, and ATR is enough to tell us that anytime that you have any well-founded tree, then you will have, and for any X, that X will have an evaluation map in the tree. All right, so ATR, as mentioned, it's one of the axioms of reverse mathematics, and it has some consequences already in reverse mathematics. One I just mentioned, that evaluation maps always exist. However, if you look at the two theorems, every Borel set is measurable and every Borel set has the property of Baire. Just look in the textbook of how those theorems are proved. And you will see that it is actually a proof by arithmetic transfinite recursion. The three so as I was mentioning at the beginning, we're interested in, can something be about Borel sets be proved by a measure argument? Can it be proved by a category argument? And we could also ask, can something be proved by ATR, right? And so ATR at least is going to be stronger than either measure or category. Or as far as what I've told you so far, they could all be of equivalent strength, but we're actually going to see that they're a little different. As a note also, because I've mentioned Borel determinacy as well, Borel determinacy, again, is a very big hammer. It actually is not even true. It doesn't even hold in second order arithmetic. The necessity of Borel determinacy, questions like that can't really be asked in reverse math. That's one of those exceptions, things that are big enough that it doesn't really fit in this model. So I'm mainly going to focus just on measure arguments and category arguments. All right, so we want to now think about how we're going to talk about Borel sets in reverse math. And importantly, I don't want to assume ATR in the definition of a Borel set, because the purpose is that we want to try to distinguish between measure and category arguments. So if we assume ATR, then we will already be assuming both measure and category can work. And so we won't be able to separate them apart from each other. So in order to consider Borel sets without having to use ATR, we define a Borel set. We say, like, suppose you have like a well-founded tree that sort of looks like intersections and unions. It's saying I'm sort of, I'm trying to be a Borel set. We're only going to call it, each individual model is only going to call that thing a Borel set if for every X, the evaluation map for X already exists in the model. All right, so a Borel set that's defined in this way is called a completely determined Borel set. And this is a way that models that are weak enough that can't necessarily always guarantee evaluation maps, they can just talk about the Borel sets that they do have, right? The Borel sets that in those models just happen to have all the evaluation maps, so they seem they're well behaved. These models may also have other sets that the model looks like, this looks like it might be a code for a Borel set. Oh, but some evaluation maps are missing, so okay, I'm just not going to count that as Borel. Just throw it away. We'll only talk about the ones that look good. All right, so if you make this definition for a Borel set, then instead of taking ATR as like a base theory for Borel sets, you can lower the base theory to another theory called L omega 1 omega, which the exact definition of it is not important for the talk, although I put it in some small type in case somebody wants to read it. But the point is that there is a sort of a base theory, what we're going to think of as sort of our small set of axioms that we are going to be happy to just assume. And the reason that L omega 1 omega CA is a nice collection of axioms is just because the facts that you would want to be true about Borel sets hold for completely determined Borel sets if you use this axiom. So we can have complements, countable unions, countable intersections, and continuous pre-images of Borel sets remain Borel using this axiom, whatever it is. Okay, so all of this slide is meant to say is that yes, we can give a notion within reverse mathematics of what is a Borel set that makes sense without ATR, and then you can now formulate the principles that every completely determined Borel set has the property of Baire, and every completely determined Borel set is measurable. And these principles just say, all right, anytime that I have a Borel set, all of whose evaluation maps are there, then that Borel set has the property of Baire. So like there exists, an open set that's equivalent to it off of a co-meagre set, and that open set is there in the model. The coding for the co-meagre set is there in the model, and a similar thing for the measurability. All right, so now we have these principles, and we can sort of summarize what is known about them now using a small diagram, which is basically that it turns out, and I'll say a little bit, I'll say just a couple words of how it's proved that both every Borel set has the property of Baire and every Borel set is measurable. Each of these are strictly weaker than arithmetic transfinite recursion, and they're also incomparable with each other. But even over RCA, both of them imply this L omega 1 omega CA, which again, if you haven't seen that before, just don't worry about that part. So you'll notice I've also put a little weak Krenig's lemma plus on the statement for every Borel set is measurable. And that's just because weak Krenig's lemma is a better base theory for saying that things are measurable, because that base theory is just big enough to tell you that the concept of measure kind of makes sense at all. So I always just add that in when we're talking about every Borel set is measurable. Okay, so I want to say just a couple of words about how these are proved, and mainly about, so this is a diagram that basically shows you that certain separations exist. Sorry, I should have mentioned that the double arrows mean that we've got a strict implication. So the fact that ATR double arrow proves that every Borel set has the property of Baire, it means that there's a model where every Borel set has the property of Baire, but ATR fails. All right, and there's also a model of second order arithmetic where every Borel set is measurable, but where ATR fails. And it happens that for those two models, also, in one model, every Borel set has the property of Baire, but it's not true that every Borel set is measurable. And also vice versa. In the other model, it's true that every Borel set is measurable, but it's not true that every Borel set has the property of Baire. So that's why it's also no implication in either direction between those. Like either one taken as an axiom, it's not going to be sufficient to prove the other one. All right, so that's sort of the content of this picture. And then I've written some words about it on the following slide. So it's a fact that anytime that you have an omega model of either one of these principles, that omega model is closed under a hyperarithmetic reduction. And an omega model, by the way, is just a model of second order arithmetic where the natural numbers of the model are the actual natural numbers. So in your model of second order arithmetic, you're really just asking what are the sets that exist. So anytime that you have an omega model of either one of these principles has to be at least pretty big as far as the sets. As I mentioned, both of them are strictly weaker than ATR. And and I didn't say yet, but let me say now, the other authors on that work are Eric Astor, Damir Jafarov, Antonio Montalban, and Reed Solomon. One can also show, as I mentioned on the previous slide, that neither every Borel set is measurable nor every Borel set has the property of Bayer can imply the other one. And one consequence that we can get already from that is remember back to that theorem that there is no Borel two coloring of the circle with an irrational rotation. So remember that that had a proof via measure and it also had a proof via category. Well, since measure and category are actually incompatible as axioms, it means that that theorem about no Borel coloring of the that irrational rotation graph, that theorem for sure we already know cannot imply that every Borel set is measurable, nor can it imply that every Borel set has the property of Bayer. It has to be strictly weaker than both. Why? Because if it could prove one of them, then starting from the other one, you could prove it and then get a proof of the other. But we know that there is no implication going from either one to the other one. Okay, but so in that example, right, we know there's the measure proof and there's the category proof. But in the other two examples that I opened with today, there were some open questions around, is there a proof by category of the perfect matching theorem? Is there a proof by either measure or category of the Borel essentially counterexample to Brooks' theorem? And so now we can formalize these questions by asking, can CDPB, every completely determined Borel set has the property of Bayer, prove either one of these? And can the CDM prove the Brooks theorem one? All right, so let me tell you a little bit about those two models that are used to do the separation. So in order to understand the models, let me give just a little bit of background or reminder about some higher randomness and genericity. So this has been studied by many folks in this community over a number of years. And the definitions that I want to give for some so-called sigma-1 generics and pi-1 randoms, these are technically actually theorems. The definition of the sigma-1 generic and pi-1 random is a little different, but this theorem is actually the useful way to approach these objects. So a real G is called sigma-1 generic if and only if G is delta-1 generic, and omega-1 relative to G is omega-1 CK. All right, so what does it mean for G to be delta-1 generic? It just means that it's generic relative to every hyperarithmetic set. And what does it mean for G to be have omega-1 G equal omega-1 CK? Well, it just means that the longest ordinal that G is able to compute is no longer than any computable ordinal. So it doesn't compute any new well orders, at least up to order type. All right, and then we have a similar definition for a real is pi-1 random, if and only if it's delta-1 random, and also doesn't compute any new well orders. So there's also something called a Van Lambalgen's theorem that holds for these higher type randomness and higher type genericity. So Van Lambalgen's theorem says that anytime that I've got sigma-1 generic, if I just computably divide it into two pieces, for example, the kth column and all columns other than the kth column, then the kth column is already sigma-1 generic relative to all of the other parts of the sigma-1 generic. And similarly for the pi-1 random. All right, so here are the omega models that we want to use in order to separate those principles on the previous slide. So the first omega model, so again, what I'm trying to do here is just tell you what are the sets that are meant to exist in the model of second order arithmetic. So if I let G be any sigma-1 generic, then I'm just going to consider like each column of G as its own like sigma-1 generic, but each column is still sigma-1 generic over the things that came previously. And now we're going to build a model just by saying, all right, start with the hyperarithmetic sets. Now throw in the first column of G and close under hyperarithmetic reduction. Now throw in another column of G and close under hyperarithmetic reduction. throw in another column, close under hyperarithmetic reduction, just keep doing this. And you will end up with a model that is basically as close to hype as possible, but you just also added all of these like very generic elements. And when you do this, it turns out that this model satisfies that every Borel set has the property of Baire, but it does not satisfy every Borel set is measurable. And if you do the same thing, but starting with pi11 randoms, then you get the analogous thing, a model where it's very close to hype, but you've added these randoms, so every Borel set ends up being measurable, but it's still not true that every Borel set has the property of Baire. And we also showed that any time that you have a model that every Borel set has the property of Baire, there have to be a lot of like at least pretty generic elements around. And similarly, anytime that you have a model of every Borel set is measurable, there have to be a lot of really random elements hanging around. So that's the way that we know that these two principles don't imply each other, because in general, the super generic things cannot compute, cannot hyperarithmetically compute super random things, and also vice versa. And it also shows us actually that neither one of those principles holds in the hyperarithmetic sets. So it turns out you actually need to have these extra random or generic things. All right, so the reason that it's significant that neither principle holds in hype is because that base theory, L omega 1 omega Ca, does hold in hype. And so in order to just briefly convince ourselves that L omega 1 omega Ca is fine as a base theory in order to study these principles of Borel combinatorics, the last thing that we just want to verify to ourselves is that these principles are not already following from L omega 1 omega Ca. Right? Because in general, you want your base theory to be small enough that the theorems make sense, but not strong enough to actually prove the theorems. Because if you're proving the theorems with your base theory, then you're not learning anything about your methods. Okay, so in order to know that these theorems about Borel sets do not follow from the base theory, we actually show that they do not hold in hype, in the model of hyperarithmetic sets. So we've shown with Henry Tausner and Rose Weishar that in hype, if we've got any completely determined and regular graph with no odd cycles, then in the omega model that just consists of hyperarithmetic sets, that graph actually will have a completely determined Borel 2 coloring. And it will also have a completely determined Borel perfect matching. So there's sort of like three layers now, right? There's the real world, where anytime that you have an n-regular graph with no odd cycles in the real world, yeah, it has a 2 coloring and a perfect matching. If you try then to make that same theorem hold, but put the word Borel everywhere, what's true in the real world is that when you put Borel everywhere, those theorems all start failing. Like all of those things become false. You can no longer find the Borel 2 colorings or the Borel perfect matching. But if instead of being in the real world, you situate yourself in hype, which is this sort of very like weak model of mathematics that doesn't actually contain a lot of the stuff that we have in the real world, then it's like the theorems, what's true in real life seems to be true for Borel sets, right? Because this hype is sort of too weak to have the objects to see that actually the Borel sets can't do it. And in particular, actually, what hype has a lot of like codes for things that look like Borel sets, like they're actually like ill-founded bad stuff. But to hype, they look like they're well-founded because hype doesn't have the paths that are through those codes. So in hype, there are lots of things hanging out that look like Borel sets but are not. And those are the things that are going to provide the 2 colorings and provide the perfect match. All right, so this is a theorem that shows that that in hype, the theorems are false. So we do need some kind of axioms, such as, for example, measure or category or ATR, or maybe even something like much bigger. And so now we have something that we can build upon. Any questions? All right, so for this talk, I wanted to talk a little bit in more detail about how the proofs of these theorems go in Hype, because you know you can do a lot of computations about like what happens in Hype, but there's maybe sort of limited amount that we care about what exactly happens in Hype, because Hype obviously is not the real world. But what we really want to know is like what's happening, for example, in this model MG or in this model MR, because that's some like context where we can isolate away. Here's like a situation where just category is true but not measure, and what can we prove like over here, and also for the other side. However, the methods of proving things in Hype actually at least somewhat similar to the methods that you would use for those models, because both those models are like really close to Hype. So I want to say a little bit about how this theorem is proved. The theorem at the top here. All right, but in order to say how that theorem goes, I have to introduce one more background, which is the theory of alpha recursion theory. So this is a method of doing a sort of a transfinite computation along an ordinal. So this actually works for any admissible ordinal, but just take omega-1 ck. That's the ordinal that we're going to always use it for in this talk. So the definition of computability like along omega-1 ck is as follows. Consider the initial segment L omega-1 ck of Gödel's constructible universe L. So if we take some subset of that L omega-1 ck, we're going to call that subset omega-1 ck CE if it's just sigma 1 in that structure. That is, there's a sigma 1 formula in the language of set theory, so that X is an element of A if and only if this L omega-1 ck satisfies that formula with X. And it's a sigma 1 formula, which means that we're looking for somewhere a witness inside of L omega-1 ck to verify the rest of the formula, which is just only has bounded quantifiers. So that means that we can understand an alpha CE set as sort of the result of a meta computation of length alpha, because what we're doing is we are imagine like increasing as beta is less than alpha, we're increasing beta because we're looking for this witness. And then at a certain point, if we find the witness, everything else in the formula is bounded quantifiers. And so whatever like segment of L had the witness, we'll also see now that the formula is true. So that'll be our definition of alpha CE. And of course, then a subset of L alpha can be called alpha computable if it's both CE and its complement is CE in this extended sense. So recall also that if you take the intersection of L omega-1 ck with 2 to the omega, you get exactly the hyperarithmetic sets. So if we want to talk about hyperarithmetic subsets if we want to talk about subsets of the hyperarithmetic reals, then we can talk about them like in this L omega-1 ck context, because those are exactly the reals that there are. So if I now look at the statements that there exists, oh, sorry, on this slide, I seem to have not written what the things are. So on this, for this second line right here, so B is some like code for a Borel set. X is some element that's supposed to be in or out of the Borel set. And then the F is supposed to refer to the evaluation map that shows that X is either in or out. And so if I say X is in with F, B, then what I'm saying is that X is in the Borel set as witnessed by evaluation map F. And similarly for X is out of B. So we see that within the context of Hype, if I look at the statement that X is in B according to some F or X is out of B according to some F, both of those are sigma 1 statements in the sense of like sigma 1 statements in the language of set theory relative to omega-1 ck, because these maps are going to be like, if they exist at all in the model, they're going to be found at some stage. And then the statement that the evaluation map is accurate, that it follows the logic of the tree, is a statement that can be made with bounded quantifier. So that means that if you have a Borel code that happens to be completely determined in Hype, right? So if it's true that in Hype all of the evaluation maps exist for every X, then in fact the statement that X is an element of B, that is a delta 1 relative to omega 1 ck statement, because there's a sigma 1 statement for the membership and in B, and a sigma 1 statement for non-membership in B. So it turns out that that is actually a characterization for the Borel subsets, at least according to the omega model hype. So we've shown that for any subset of hype, the following are equivalent. There is a completely determined Borel code for A in hype. There's a determined Borel code for A in hype. Okay, I didn't tell you actually what a determined code is, but it's basically one where instead of having to have a full evaluation map, you just have like a partial evaluation map that has enough stuff in it to convince you that X is in the set, even though maybe you didn't fill out everything. And both of these in hype are equivalent to saying that A is omega 1 ck computable, or in other words, delta 1 relative to L omega 1 ck. So the reason that this is useful for proving things in hype is because now we can apply these omega 1 ck computations in order to prove theorems about Borel sets in hype. So the definition that I gave on this slide looks just very static. You know, you have the two sigma 1 definitions, but there's also a dynamic way to think about these omega 1 ck computations that's very useful for understanding what's going on in hype. So recall, so here I've just copied the definition of omega 1 ck computable. There are two sigma 1 formulas, one of which tells you that X is in a set and the other one that tells you that X is out of a set. And we can write them explicitly as, we're sort of looking up through omega 1 ck to try to find a witness in some L beta. And it's a well-known fact that uniformly in beta, if you have enough jumps of 0, then you're able to compute a model of L beta. So therefore, one way to think about a set being omega 1 ck computable is that there is some fixed computable procedure that you're going to, on input X, give the procedure higher and higher and higher and higher amounts of jumps of X. And so maybe all this is happening, kind of simultaneously. You imagine that you have as much oracle power as you need at each stage in order to say all right, let's say that I put beta jumps of X into this oracle. Is it going to actually tell me something? No. Okay, now I'm going to try beta plus 1 jumps of X. Right. So you have a computation that goes along like this, and if a subset of hype is omega 1 ck computable, then that means that there is some computable functional gamma, where if I keep feeding the higher and higher jumps of X into it, eventually I will see, all right, here is enough jumps of X that now it converges, and it's going to give me the answer, whether X is in or out of the set. So that's how the omega 1 ck computation works. And we can use that now in order to more intuitively give the constructions to show that various things happen in a Borel way in hype. Okay, so first example, in hype, there is a completely determined Borel well ordering of the reals. Why is this? Well, it's a true fact in hype that you can kind of well order the elements of hype by sort of a lexicographic ordering, where first you say, all right, what is the least ordinal that I need in order to compute each of these guys at all? And if one of them needs a smaller ordinal than the other one, then that one will be smaller. And if the least ordinal, if the least number of jumps of 0 that is able to compute both of them is the same for both, then you can break the tie by using what functional is used in order to compute them. So that's a natural well ordering of the hyperarithmetic sets. And this well ordering is omega 1 ck computable, because if you give an X and Y to start with, and you just start taking more and more and more jumps of them, well, you're also getting more and more and more jumps of empty set in the process. And eventually you're just able to see, oh, okay, what was the least ordinal that was able to compute each of these guys? And then compare the ordinals, compare the functionals if needed. With enough jumps in a uniform way, you can do that. So there's an omega 1 ck computation to figure out this ordering, and therefore in hype, it's going to be able to be done using a completely determined Borel set. So in Hype, there's completely determined Borel well ordering of the reals, which is already like pretty poorly behaved. But you can use this in order to prove some graph coloring theorems or non-theorems in Hype. So just remind you, so Marx showed that contrary to how it is in the real world, for every n greater than or equal to 2, you can have an n regular acyclic graph that does not have any Borel n coloring. And there's sort of two ways. There's sort of two ways that that things go in Hype, and it's actually a difference depending on whether or not we actually make the graph n regular or not. So on the one hand, we can show in Hype that every n regular graph with no odd cycles has a Borel 2 coloring. However, if we remove the assumption of n regularity, then we actually end up with an acyclic Borel graph such that every vertex has degree at most 2, but nevertheless, we're not able to 2-color the graph. Right? So in Hype, sort of two different kinds of things happen. When the graph is known to be regular, then Borel things behave the same as like real world non-Borel things. But when the graph is not regular, then Borel things seem to behave more like actual Borel things behave. So let me explain the distinction here, what's going on. I'll give the proof of B. This is a very short proof, and it uses omega-1 CK computations to make Borel things. So we want to make an acyclic Borel graph that basically diagonalizes against all possible Borel 2 coloring. So in other words, we are going to perform an omega-1 CK length computation that's making a graph and diagonalize against all of the computations that anybody else might be doing. So in order to defeat the ETH omega-1 CK computable coloring functional gamma E, what we're going to do is at the beginning of time set out 2 vertices that are not connected to anything, and just as long as the opponent doesn't color them, just don't connect them to anything. But then as the stages go on and we get more and more jumps of these elements, eventually potentially the opponent colors both of them. And if the opponent does color both of them, now we can respond by adding either 1 or 2 more vertices and connect them either with an even or an odd length path in order to make the coloring that the ETH functional did incorrect. And the reason that this works is because in the game between the graph builder and the graph colorer, the graph builder has the upper hand because the graph builder is free to not connect those vertices ultimately if the graph builder chooses. Right? So I can say, no, I'm just not going to connect these to anything. Their degree is going to be 0. Oh, actually, just kidding. Their degree is 1 at an arbitrarily late stage. So why does this not work if the graph is n-regular? Well, what n-regularity gives us is essentially it gives us a way to catch our tail on every connected component. So if we've got a Borel n-regular graph, then claim for every vertex, if we take enough jumps of that vertex, we will eventually reach a point where we can compute the entire connected component of that vertex. And the reason for this is just because if the graph is actually n-regular, then for every vertex and for every k, which is like sort of a distance like away from that vertex in the graph that we might want to go, there is in fact a almost unique like finite object, which just consists of all of the vertices that are within distance k of the given vertex, and all the evaluation maps that that show that. And if you are guaranteed in advance that the graph is k-regular, then once you see that object, which is just a union of finitely many hyperarithmetic things, so that is some hyperarithmetic object, and once you see it, you'll recognize it because you'll say, oh, everybody in this object actually has k edges coming out of, actually has n edges coming out of it. So because there is an arithmetic way to recognize when you have these like bigger and bigger like neighborhoods of your vertex, you can in a sigma 1,1 way describe the ordinals that are needed in order to get more and more of the connected component, and then apply sigma 1,1 bounding in order to guarantee that at a certain point you're going to have the whole component. So that is something that you can't necessarily guarantee in a uniform way in the previous case. All right, so then once you have that, and I know I'm close to out of time. It looks like I have a lot of slides, but I don't, because I put extra stuff after the references in case there would be something, but we're definitely not going to go there. So, so now using this regularity thing, why we can always find the, why does the colorer have the upper hand now? Well, given a vertex, the colorer is now actually free to wait until the entire connected component has appeared. And once the entire connected component has appeared, the colorer can recognize, all right, this is it. I got the whole connected component. And then once you have the whole thing, now you can color it and the graph builder can no longer respond to you. All right, so that's kind of the difference between regularity and non-regularity. And you can do a similar thing with perfect matching. And I won't do the details on that because in Hype, it's kind of the same thing. You wait for the whole component, and then you have some arithmetic method to get the coloring on just that component. I want to finish because I think, do I have 1 or 0 minutes left? Yes. Yes. Okay. I'm just gonna. So this is a repeat of the previous slide, just reminding you what's Hall's theorem. So then I just want to wave my hands about what happens when you try to take this same idea and go into the model MG, right? So the model that's almost like Hype, except you have these like little generics hanging around. So in a very rough way in MG, you can still run these omega-1 CK algorithms on X inputs and have the resulting like things that you're able to compute by those algorithms be Borel set. But a lot of the things that were useful in Hype, we lost it, right? So there's no longer an ordering like on the elements of a connected component. So just, oh, find the least element of a connected component and color like according to that is not gonna work anymore. This is actually not too big a problem though, because things are still close enough to Hype and you still have that well ordering on Hype in an omega-1 CK computable way. The more important thing that's lost when we go to MG is just a general assurance that at a certain point we are going to have the whole connected component. At least if the an initial graph is weird. If the initial graph is actually truly well-founded, then you still will have that. So this is kind of a work in progress that I was going to say more words about, but I think that for the reason of time, I'll just mention that this is kind of what the obstacle is when you try to go to these MG or MR, which is like trying to really get a handle on the whole connected component in the course of doing this omega-1 CK algorithm. So I will stop here and, oh no, I will stop here and thank you very much.
Thank you very much. So is there any question? So first.
You mentioned Mark's result using Borel determinacy. Did Andrew or you with your work, does it give any insight on what is the necessary use of? I mean, you know, if you go level by level, if you that if you want to prove this for sigma 0 alpha, and you want to say there is a Borel at alpha level, what use of determinacy do you need? Because you were saying that you don't need all of it, but every time there's a result like this using Borel determinacy, we can try to figure out how much do we use of Borel determinacy.
Yeah, so I can't answer that question in full, and Andrew Marks would be the best to ask about, certainly not about the like level by level. However, I can remark that so it's been observed actually by Sherwood Hackman that in this context of like graph coloring stuff, in the larger like set theoretic context, the full Borel determinacy cannot be like fully needed. So it is like somewhat weaker than Borel determinacy. And if someone wants to talk more about that after, I can share that argument of Sherman that Andrew shared with me.
Yeah, so just a very basic question. So for example, there is for coloring, there is an obvious more or less thing that if you have a graph as an oracle, you sometimes cannot compute the coloring.
Mm-hmm.
And this is it somehow related, or is it just much more trivial and has nothing to do with this? So also, if you just consider different combinatorial problems, for example, you know that for finite sets, 2 coloring and 3 colorings are completely different categories. They are polynomial and complete. And does this low-level facts, do they have some intrinsic connection with your result? For example, can you expect that something which is more difficult in finite case, like 3 coloring, would be much more difficult in this case in terms of high level difference?
So for your second question, I don't know about the finitary difference in its relation. For the first question, I'll go back to the perfect matching slide because this is actually one example of that. So in general, given a graph, if you just have imagine you have a countable graph and you have an oracle for that graph, you may not necessarily have a computable perfect matching for that graph. However, the collection of all perfect matchings forms a pi01 class, at least once you have a place to start. At least once you have a presentation of the graph, like an oracle. So because it is a pi01 class, you can always, if you have that oracle for the component, you can just take the leftmost path with one additional jump. So if you're trying to do an omega-1 CK computation, the fact that there's no path computable in the component doesn't really enter into it as long as you just have some hyper-arithmetic way to get to the object. The more difficulty that's encountered in this context is the fact that it's hard actually to get that presentation of the component. That's where you have to do the work to do some argument to say, in fact, even though the set of vertices is this very large, complicated thing, I was able to extract from it a countable graph that refers to a single component.
Okay, any other question?
So in your definition of the generic sigma 1 generic set, so you had 2 requirements, that it's delta 1 generic and also that the ordinal doesn't go up. Is it easy to show that there is a delta 1 generic where the ordinal does go up? The first non-computable.
I am.
Yes. Just say yes.
Yeah. Okay, go ahead. Go ahead, Liang. Why is it easy to see?
It's in our paper with Anjani's and Chita.
Well, I know that. She asked, is it easy to see?
Okay. It's not easy to see. Okay.
Okay, thank you very much. Is there any last question?
It's in this paper, Chang, Nice, and Yang, 2008. You can read read it.
Okay. So if there are no more questions, so let's thank the speaker again.